Okay, section 6.3 is named after something called the central limit theorem, which has to do with, well, it has to do with sample means and how they relate to population means. Now remember the difference between a sample and a population. The population is the whole big group of everything that you care about. And then a sample is a smaller group chosen from among that population. So if we had a big meadow full of flowers, and we knew that the average height of all the flowers in the meadow was 15.5 inches, that would be the population mean. And the symbol for that is that Greek letter mu. If you went out and gathered, say, a dozen flowers out of the meadow and just measured the heights of those 12 flowers and then calculated the mean, the average height just for those 12, that would be a sample mean. And the symbol for a sample mean is x bar. And then sampling error refers to the difference between something you calculated from your sample and what you would calculate if you were using the whole population. So in this sense, the word error doesn't mean that somebody made a mistake. It refers to like how far off you are when you're trying to estimate something or compare something to something else. So the central limit theorem says that, well, here's the official statement. But it says that if you take a big enough sample, and then you take another sample and another and a whole bunch of samples, and you look at what happens with your samples, and you look at the sample means for all those different samples, they would tend to follow a normal distribution. And the mean of that normal distribution for the sample means would be the same as the mean of the whole population. And the standard deviation of those sample means would be sigma over the square root of n. It would be the standard deviation of the whole population divided by the square root of the sample size, how many individual flowers or whatever you have in your sample. So if I told a whole bunch of people, go out in the meadow, pick a bunch of flowers, measure the heights of your flowers, and calculate the average height of the flowers that you picked. So that's your sample mean. Everybody's going to get a different sample mean. And then I take those sample means and I average those together. The average of those sample means should be mu, pretty close to the mean for the whole population. And the standard deviation of those sample means should be sigma divided by the square root of n. Sigma stands for the population standard deviation, and n stands for the sample size, how many flowers you all had in your samples. And the reason that's important is that when we calculate z-scores based on not individual values, but sample means, instead of just doing x minus mu over sigma, we're calculating x bar minus mu over sigma divided by the square root of n. So the problems in this section are going to be similar to the last section, except that they're going to be questions about sample means rather than individual values. So this first example is already worked out in your notes. So rather than explain this one, let me skip ahead to another example and work through that for you. So assume that the mean systolic blood pressure of normal adults is 120 millimeters of mercury. That's just the units that blood pressure is typically measured in. And the standard deviation is 5.6. So we got our population mean and our population standard deviation, our mu and our sigma. Assume the variable is normally distributed, so we can base this on the normal distribution. And now this is a two-part question. Part A is exactly the kind of problem we were solving in the last section. If an individual is selected, just randomly selected, find the probability that that individual's blood pressure will be between 120 and 121 millimeters of mercury. And then looking ahead to part B, that says if a sample of 30 adults is randomly selected, find the probability that the sample mean, the average blood pressure for those 30 people, will be between 120 and 121.8 millimeters of mercury. So in part A, we're trying to find the probability that one individual value is between 120 and 121.8. In part B, we're finding the probability that a sample mean is between 120 and 121.8. So first let's do part A. Remember how that works. We have to start by taking these numbers, the 120 and the 121.8, and converting them to z-scores. So for 120, we take 120 minus the population mean, which was also 120, and we divide by the standard deviation, which is 5.6, and we get 0. So for 120, the z-score is 0. For 121.8, 121.8 minus 120 divided by 5.6 is 0.3214, and for z-scores, we like to round to 2 decimal places, so I'll say it's about 0.32. So the probability that x is between 120 and 121.8 translates into the probability that z is between 0 and, what was it? 0.32. Remember what happens next? We look these z-scores up on table E. So when I look up 0.32, I get 0.6255. And when I look up 0.00, I get 0.5000. So now I just have to subtract 0.6255 minus 0.5000 to get my final answer, which is 0.1255. Now in part B, this works almost the same, except that when we convert these numbers to z-scores, we're using the formula for the sample mean, the x bar minus mu over sigma divided by the square root of n. What's n? N is, well, in this case, it's 30. In general, it's the sample size. It's how many individuals you have in your sample. So we need to convert 120 and 121.8 into z-scores using that formula. So the 120, we take 120 minus 120 divided by 5.6 divided by the square root of 30. And that comes out to just be 0. Now we've got to convert 121.8. So here's how it goes into the calculator. Parenthesis 121.8 minus 120, close parentheses, divided by parenthesis 5.6 divided by the square root of 30. And I'm going to get out from under the square root sign, close parentheses, hit enter. But notice I put parentheses around the x bar minus mu, 121.8 minus 120. Then I divided by, and then I put parentheses around the sigma, which was 5.6, divided by the square root of n, which was 30. And that came out to be 1.76. Now I got to look those z's up on my table. When I look up 1.76, I see 0.9608. 0.9608, and when I look up 0, I get 0.5000. So 0.9608 minus 0.5000 gives me my answer of 0.4608. So there's about a 12.5% chance that an individual would have blood pressure between 120 and 121.8. But there's around a 46% chance that if you've got a whole group of 30 and average their blood pressures, their average, their sample mean, would come out to be between 120 and 121.8. Now, just as in section 6.2, there are shortcuts that you can use. If you have a graphing calculator, you can ask it for normal CDF, give it a lower number of 120 and an upper number of 121.8. The mean is 120. And for the standard deviation, we're going to put in 5.6 divided by the square root of 30. That whole thing goes in for the standard deviation. And it gave us an answer of 0.4608. And if you want to use that that thing on the web, that normal distribution calculator, put in for the mean, it's 120. And for the standard deviation, well, we might have to go back and calculate this ourselves so we can put in the right number. It was 5.6 divided by the square root of 30. And that's about 1.022. And now we want the kind of problem where it gives us the probability of x being between 120 and 121.8. And when we calculate that, it shows up as 0.4609. We probably got a little bit of round off error because I rounded off the standard deviation, but real close, about 46%. So that's the answer.